So let's recap a little bit the results that we achieved last time. So we have Keynes equations for a system of MB rigid bodies. Okay. We saw that basically in vector form it could be written as such. So f equal to 0. Or in component form, we could write Fm, which is equal to the sum of E going from 1 to the number of bodies MB, of F, which is the resultant vector coming from the sum, or the difference, if you want, between the resultant of external forces and the rate of momentum times dm. Okay, with m going from 1 to ni, number of independent parameters. So f is, as we said, the difference between the result of our external forces and the rate of the momentum for the body I. And Vm is the partial velocity vector. Now, under two simplifying hypotheses, that's to say, all of the Q's, so all of the Lagrangian parameters are independent. And the second one is that basically we take the generalized velocities as motion parameters. So basically we have that the motion parameters, are basically identically chosen to be the qm dot. So motion parameters equal to generalized velocities. Then we have a simplified form of Keynes equation where the partial velocity vectors become equal to the partial derivative of the position vector I with respect to qm. Okay? Okay, so this is where we basically arrived last time. So this is our general form. And this is the simplified form, okay? All right, now let's make an example in which we give a little bit more of insight on the significance of all these formulas and how they are actually relevant for our case. So again, we have an example. I should have again the image. I think it should be this one. Yeah. So here is the now well-known example. We have basically that in this case, our Q, if you remember, were the angle theta and the distance Q. Okay. And in this case, we have that all of the Q's are independent. Did you remember that? There are no constraints enforced in this case. So no constraints to enforce. Okay. So it means that in our case, this is first. This is the first thing, which comes as a consequence of this one. And the second is that we choose the generalized velocities as motion parameters. Okay. So this means that we can, in fact, implement the simplified approach, okay, the simplified formulation. So we can make use of the simplified Keynes equations. Okay, which become, well, as we have said, Fe, right? In this case, we have only one body. Okay, so I will omit the superscript I minus P dot scalar Vm, right? Oops. That's our equation, equal to 0. Okay. For m equal to 1 and 2. Okay, because we have two independent coordinates. So it means that basically our equations are the following. We have Fe minus P scalar the partial derivative of P with respect to theta equal to 0. That's the first equation. And the second equation is, again, the resultant of the external forces minus P dot times the partial derivative of P, the position vector, with respect to Q this time, equal to 0. Two equations, because we have two independent coordinates. All right. Now, if you recall, we have that let's refresh the expression of these quantities. So we had that Fe, if you remember, was equal to minus t over q times the sinus of theta minus mg plus t over q times the cosinus of theta, and then we had 0. Huh? Then we had, of course, that our position vector was equal to cosinus of theta, sinus of theta 0 times q. And p dot, the rate of the momentum, if you remember, this was m theta double dot q plus 2m theta dot q dot, all multiplying minus sinus of theta, cosinus of theta, and 0, plus m q dot, double dot, multiplying cosinus of theta, sinus of theta, and 0, plus m theta dot square q, all of this equal to minus cosinus of theta minus sinus of theta and 0. Okay? Now we have the V1, which, as we have written, is the following. Well, given our expression of P there, we just have to do a derivative, okay? So dP over the theta minus sinus of theta, cosinus of theta, 0, times Q. Okay? This is the first one. You see, we have only to do a derivative here. The second is well, it's very easy as well. There you go. You have the two partial velocities. Now we only have to do the scalar to obtain the equations. Okay. We will do it now. No, perché è una derivata rispetto a θ, non rispetto a t. Ok? Chiaro? Ok. So our equations of motion so it's basically, I'm just rewriting this one. Huh? Now that I have everything here, I'm just doing that. This scalar product. In a quite straightforward way, which are exactly the same that we have already derived a couple of times previously with the help of D'Alembert's equation and then with Lagrange equations. You see, this was quite straightforward to resolve, right? You see, it basically is just a matter of doing these derivations and doing the scalar products. And that's it. There is no all of that, somehow cumbersome steps, algebraic steps, mathematical steps that we have to implement. Once you have identified the parameters, you basically have your equation derived in a quite straightforward way. Okay. So this is just a hint to the power of such formulation. All right. Now, once this is done, we will derive a new set of equations, which are basically, we will open a new chapter, which is the last chapter of the dynamics of rigid bodies. We will derive the equations of Newton-Euler for rigid bodies, for a system of MB rigid bodies. And this will conclude the dynamics of rigid bodies. Then, after that, we will include in our formulation the effect of deformations, okay, that will, add complexity to our treatment, okay, because we will have to consider also the fact that in order to be able to describe the dynamic of a body, actually the dynamic of a system of bodies, these bodies not only can translate and rotate, but they can also deform while they are moving, okay, so you can understand that the treatment, the formulation will be more complex than this. And with this respect, in the notes, you will find that I inserted some, recaps to previous concepts that you already have gone through with other courses, which will compose basically chapter 3. Okay, so we are here in chapter 2, and we will conclude it probably tomorrow. Then there will be chapter 3, and chapter 3 will be only on the mechanics of deformable bodies, without including any kind of body-free motion. And all of the concepts that will be included in chapter 3 will not be part of the exam. But since we will be using some of the concepts presented in chapter 3, I put this in the notes so that we can speak the same language and we can call the same things using the same names. Okay, can also be useful for you to do some review of those concepts. Okay, so let's start the last chapter of this dynamics of rigid bodies, developing Newton-Euler equations. This basically will put together all of the things that we have seen so far. So, equations of motion, again. Of MB rigid bodies. Why they are called Newton-Euler? Because basically they were developed by the two, okay? Independently, so basically they got both the names. All right. So we start again for a system of MB bodies with our well-known definition, okay, of the position. This we know already by heart, okay? If this is true for the position, then for the velocity, we have seen that we saw it for particles, but now we implement it for bodies, because remember that for the difference between particles and bodies, at least from a rigid point of view, is that particles cannot rotate. Okay, so they do not need to parameterize their orientation, while for bodies this is necessary. Okay. Okay. And this we saw could be written as such: minus AI R0 with a tilde. This is a skew-symmetric matrix. Okay. Where, okay, of course, this can also be rewritten as a matrix form as the identity matrix. Let's write it properly. Minus A R0 tilde GI applied over a vector of components R dot and theta I dot. Okay. Where basically this, if you remember, was a skew-symmetric matrix written as such: R0 3 I minus, sorry, R02 I. Then we had R03 I 0, R01 I minus R02 I, R01 I, and 0. Okay. Basically, this was a matrix coming from the components of the vector R0 here, okay? Built basically to express a matrix product, a vector product. And this, if you note it, this last vector is basically our Q dot. So as generalized parameters for a body, for a general body I, we take into account the position of its center of the local frame, and then, for example, Euler's parameters. Okay. So in this case, this can be either a 6 times 1 or a 7 times 1, okay, vector, depending on the parameterization. This means that the kinetic energy, which we call Ti, of the body can be written, making use of this. We already know it. Okay, we have come a long path from here. So T is equal to what? For a particle, if you remember, was 1 over 2 of m of the particle, and then there was basically the scalar product between the velocities. But here we have a body, so it's something which is not, a pointwise entity as a particle. It has some volume, so we cannot write generally m, but we have to undergo through an integral over the volume, right? And then call in the density, rho, rho I, times what? Well, the velocity transposed times the velocity itself, okay, in the vi. Okay. Now, we have all of it here because we know how to express this velocity, this position velocity, sorry, this velocity vector here. So let's do it. Yeah, let's do it like this. So we have r dot I transposed, and then we have theta dot I transposed, like so. Then we have the integral, we have the density, and then here we have I, the identity matrix, transposed. Just a second. Yeah, okay. Transposed ng I transposed, okay? Times I, and then minus, so this is, so to make it clearer, so this is not a single vector. See, this is a two parts, okay? So this is made out of two parts. So I'll rewrite here the same thing. The v, the y, times what? Q dot. Okay. So here, basically, I'm adding this last part, which is r dot I, q dot I. So sorry, theta dot I. Okay. So basically, what I did is just nothing different than inserting in here, in the definition of p dot, this definition here. Okay, this is what I did. And in doing so, I put q dot outside the integral sign, you see, because this quantity, q dot, being generalized coordinates, they only depend on time. You remember that, right? Is it clear also from home?
We lost the voice slightly at the end.
So should I repeat it?
Yeah, just the last part.
Yeah, so basically what I'm saying is that, you see, this q, they are only a function of time. So in this sense, when I do the substitution here, I can put it outside the integral sign because the integral is an integral over space, over the volume. Okay? So that's why in here, you see the q dot, in here and in here, they are outside of the integral sign, which ends here. Okay? Okay. Is it clear now from home?
Yes, Prof. Thank you.
Okay, okay. So this is equal to something that we can rewrite like so. Ti Q dot transposed over a matrix that we call M I like so. Where this Mi is again the integral over the volume of the density times yeah. Okay, all of this. Okay. Now, this matrix, you see, is basically formed out of, you see, if I do the same here, and you divide this matrix in sub-blocks, it can be, basically, this is a 2 times 1 blocks, and this is a 1 times 2 blocks. So eventually, your matrix is a 2 times 2 blocks. Okay? Okay. So we can rewrite it as such. A submatrix M lowercase r theta. Then we have M r theta again, but transpose this time, bless you. And then M theta theta. Right? And this is the mass matrix of the body number I. Okay. That's what you call mass matrix of a rigid body. Okay. And you see, it is composed of 4 submatrices. Of course, it's symmetric. We will see it right now. Why is it symmetric? Well, from a mathematical point of view, it's quite straightforward because basically it's the product of one matrix times its transpose. So it must be symmetric. Okay. In fact, this and this one are one the transpose of the other. Okay, because this one basically is I times this, while this is this times I. Okay. These that we will see now are the submatrices which are associated to what? This one is the one associated to the rigid motion here. This one here, rigid motion, and we will see. This is associated, in fact, to the coupling that can happen in certain cases between the rigid motion and rotation. Okay? And on the other hand, this one here is the mass matrix associated to rotation. okay, of the body. Let's see how they are composed. So we have MRRI, which we can therefore define as V okay, that's what it is. So now if I do this, what do you think we can get? Well, it's basically each one of these, it's 3 times 3, no, matrix, in which basically we have that each one of the of the principal diagonal elements are nothing different than the integral over the volume of the density of the body. Okay, so they are what? They are the total mass of the body. Okay, this mi scalar 0, 0, mi. Okay, where mi is the total mass of the body. Okay, why do you think, why do you think it has this kind of structure, if you think about it? No? Well, you should notice this. Why did I call it MRR? There is a reason with the subscript R, because this is what is associated to the first 3 components of Q. You remember here when I define the Q dot, and therefore the Q, they are defined basically associated to R. And R is something which indicates the position of the center of the origin for the local frame. And it's basically associated to the translation, okay, of the body. So if this is true, why do you have this kind of structure for the mass matrix? Can anyone guess? What's the physical meaning of that, apart from the mathematical derivation? 3 directions are independent, but more than that, and this is true, when you move along x, y, and z, you move together with all of the mass. So the portion of the mass that is involved into translation along x, y, and z is all of the mass. That's why you have the total mass of the body, okay, in the diagonal. That's the physical meaning. This is something that we should have expected. Okay? All right. So this is...
Prof, can you please repeat that? I did not understand.
Yeah. So what I said is that the reason for which we have, the total mass of the body in each of the 3 elements of the principal diagonal of the matrix is that when you perform a translation, okay, along x, y, or z, it's the overall mass, it's the total mass of the body that participates to such motion, okay? That's why you have all of the mass, the total mass of the body in 1, 1, 2, 2, and 3, 3 of this mass, okay, of this matrix, sorry.
Okay. Yes.
Okay. So this is the sub matrix associated to translation. Okay. Then we have M R theta I. And this, if you remember, is minus the integral over the volume of rho I. AI R0 then G dot. Okay. Now we can also, of course, do the following here, since again, A does not depend on the volume, okay, on space coordinates. So we can write basically the following. So this doesn't add much, but you see, if you remember how R0 with a tilde is composed, the matrix, you will have that this matrix here has the following form. This is a 3 times 3 matrix, which is basically done as the following: rho I, the density over V of rho I. And then here, okay, here is basically 0, sorry, because this is a skew matrix. So here we have 0, 0, and 0. But for example, here we have, in this component here, we have minus the integral over rho, sorry, over Vi of rho R0, 3 in the Vi, okay? And then something over here, similar. What do you expect from this kind of integral? I mean, this is the integral of an odd function, you know? Huh?
0?
Yeah. Come again?
Because it's an odd function, it'll be 0.
Yeah, it's an odd function over a volume, okay? So it's a static momentum, as someone in the class from the class was hinting. So what happens when you integrate an odd function over a domain which is even? What does it happen? I'm saying, so this function here, R03 over bar, is something of the sort. R03I, something of the sort. No? It's a linear function. So what happened when I integrate it on a domain that is even, like here? So this is, I don't know, A, and this is minus A. For example, this is the coordinate x3, whatever. So this and these are the same and opposite, because the integral is an area with sign, if you remember. So it means that the integral of an odd function like R03I over an even domain is 0. And when this domain becomes even, because this integral is done over the volume here, no? It becomes even when I take into account the origin of the local frame coinciding with the center of mass. So if I place my local frame in correspondence of the center of mass of my body, all of this submatrix vanishes. Okay? Which means that there is no coupling between translation and rotation. This is something well known, right? Okay. So if the origin of my body frame at the center of the body, my submatrix MIR theta vanishes completely. Okay. Okay. Now let's check the last one. M theta theta. M theta theta is basically some matrix associated to rotation. In fact, we can write it as follows. The I of G I transposed times R0 transposed over R0 I times G I. All on this has to be integrated in the volume. Now again, since the matrix G, as you remember, is basically composed of the Euler's parameters, for example, is only dependent on the orientation and not on space, not on the position, we can rewrite it as follows. Okay. And typically, we define as I theta theta with an overbar this quantity between under integral sign. Okay, and this is called, how is it called? Do you know? Tensore di inerzia. Okay, this is the inertia tensor of the body. Okay. So let's take a look at how this is done. It is composed, and then let's make a couple of observations. So we have basically that is composed as such. So we have I11, then we have I12, I13, we have all the components, I over bar 22I, 23, and 3, 3. In here it's symmetric, okay? Of course. Now, in the components here, these scalar components of the inertia tensor are called like so. So if I is equal to j, then we have what are called the moments of inertia, okay? While if I is different from j, we have the products of inertia. Okay. Now, I would like you to notice two things. First of all, since the body is rigid, the tensor of inertia is what? It's constant in time, right? Because basically, you see, from here, we have that since R0 over bar is a constant vector, R0 over bar tilde is a constant matrix, and therefore also the inertia tensor is a constant tensor, okay? So this one we can write like this. Is constant in time. Of course, you can already anticipate that when we will, dealing with deformable bodies, this will be changing in time, and that will add a lot of complication. Okay, but for now, this is the thing. One additional observation that I would like you to do is the following. So take a look at these some matrices here, MRR. This is constant in time, no? As long as the body is not, acquiring or losing mass, this is constant in time. Okay. This one here as well, typically is 0. Okay, but if not, would it be constant in time? Any guess? From home as well, huh? Look at the components. Are they constant in time or not? Do they vary in time? Here, look at this. Well, I would say that A, matrix A depends on the orientation, so on the angles, and G as well. So typically this is time dependent. Okay. One additional thing, in fact, here I said that if the origin of my body frame is located at the center of mass of the body, this submatrix is 0. This implies not only that I'm in the center of the mass, in the geometrical center, This is true only if the body is also homogeneous. Okay, so it means that if the body is homogeneous, the center of mass coincides with the center, the geometric center. Okay, but nonetheless, even if it's not homogeneous, as long as I can detect the center of mass, if I place there my origin of the local body frame, then this submatrix vanishes. Okay. Now here, this of course as well is not constant in time. So this is time dependent as well. Okay. Not only it is time dependent, but it also depends on what? It time dependent, of course, but it depends on the cues, right? On the angles. And how is it this dependence on the cues implied in this expression? Is it a linear? Is it a linear dependence or not? If you remember the G basically are composed of the θ0, θ1, θ2, and θ3, of basically the 4 Euler parameters. And the Euler parameters inside, they have the sinus and the cosinus of the angles. Okay? So it means that this one here, m theta theta, he shares a nonlinear dependence on the cues. Okay? Nonlinear dependence on the thetas, okay, on the orientation, not on the position, in fact. So it means that our mass matrix for the body is non-constant in time, even if we are only taking into account a rigid body. It's non-constant in time and has a nonlinear dependence on the orientation, or in general on the generalized parameters Q. Okay. Even in the simplest case. Okay. So this is important. With this in mind, we can derive the following. So our Ti, so the energy, the kinetic energy of the body, can be basically rewritten as one component associated to translation, one component associated to decoupling between rotation and translation, and one associated to pure rotation. Okay. So okay. Then we have T r theta. Well, we can call it like that. Yeah. Like this. to rotation. Okay? Okay, this makes no surprise. We can also rewrite this one here, the last one, like so. Introducing basically the inertia tensor. Huh? Okay. And this one here, for what we have already seen, is omega with an overbar. Okay, so G theta dot, if you remember, was omega. Okay, this we have already seen. We can also write the following. So we have that omega over bar is equal to A transposed omega. Therefore, Ti, theta theta, can be also written as omega I, AI, okay. And this one here is typically referred to as, again, the inertia tensor, but this time referred to the inertial frame, okay? Okay, so this is the inertia tensor. Well, let's say written in terms of inertial quantities. Okay, because as you should know, a tensor and the vector is a tensor as well. They do not depend on the frame of reference which we adopt. Okay, but their components do. As a vector, right? When I have a velocity vector, no matter where I actually describe it, it always stays the same. It's always the same vector. But its components depend on the reference frame which I adopt to describe it. Okay. All right. All of this was needed for one reason, for the following reason. Okay. We now consider a system. So all of that we have written so far is for the generic body I. Okay. Now we consider a system of n B bodies with no constraints This is the first case, the simplest case, in which all of the coordinates are independent because there are no constraints equation to enforce. If you want, we can call it like this. So our Q becomes what? Becomes the following. We have Q1, then we have Q2, until Q and B. No? It's the sum, is basically the vector of all the generalized coordinates of each body. The mass matrix of the overall system becomes, yes? Okay. Is done like
quick question.
Yeah, just let me finish this one. So we have 0. So this is the matrix, the mass matrix. The overall system. Okay, go ahead.
What happens to kinetic energy of r theta, the translation rotational coupling, if we take it with respect to the initial reference frame?
If we take it with respect to what?
Inertial reference frame.
It stays the same, of course.
As opposed to the center of mass, which made it made the value go to 0.
No, wait a minute. So if we consider the local frame, the body frame centered in the center of mass of the body, then the mass matrix simplifies and the diagonal blocks vanish. Okay, that's what happens. But then eventually your expression of the kinetic energy is always the same, is this one. Okay, then again, if you apply this particular choice for the origin of the local frame, this vanishes, and the energy that can be included in here goes here and here. Okay, so that basically no matter what you do, no matter from where you describe it, of course, the kinetic energy of the system, which is a physical quantity, has to stay the same. Okay, this is clear. Huh? And in fact, it is represented by a scalar, which is a tensor of order 0. So it means that, as we were discussing before, it doesn't depend on the frame that you take into account to describe it. Okay? So depending on the way you describe it, these three components here, can vary, but the sum must stay the same, because each of these three components depend on the way you describe the motion of the body. But then the sum, again, has to stay the same, because it's a physical quantity. It doesn't depend on the way you describe it. Okay?
Okay, but if the frame is moving with respect to the body, then wouldn't that affect the kinetic energy?
No, because if you go back and you see the definition that we took into account at the very beginning of our lecture here, or actually even before, here, oh, sorry, this one here, the kinetic energy is defined with quantities directly expressed in the inertial frame. P is the velocity of the body in the inertial frame. Okay?
Okay.
And the inertial frame stays fixed because it's an inertial frame.
Yeah, yes, with respect to inertial frame, it stays fixed. But,
no, the inertial frame is a fixed frame.
Yes. So what I mean to say is, with respect to inertial frame, the kinetic energy stays fixed. But if there is a frame which is moving with respect to the inertial frame, so it's also moving with respect to the body frame, then with respect to that frame, the kinetic energy must change, right?
No. It's changed in the, so what we are doing here is the definition of a quantity, it's a physical quantity, which is the kinetic energy possessed by the body, which is moving with respect to our inertial frame. Then we are using the body frame to make a smart description of this quantity, and this description leads to basically the definition of these three subcomponents, okay, of the kinetic energy. This one here, TRR, TR0, T theta theta. And these three components, as I said, depends on the description that you do of the motion of the body. So if you describe the motion of the body with respect to a local frame, then of course these three components will vary, okay? But again, the sum of this must stay the same because it's a physical quantity, it cannot depend on the way you describe it, okay?
Okay, so the total kinetic energy is always defined with inertial reference frame, which is constant.
Yeah, of course.
Okay.
By definition, by the definition of inertial frame.
Yes.
Okay.
Thank you, Professor. I understand.
Oh, no problem. So this we were saying. So this is the mass matrix of the overall system, and so we define the total kinetic energy of the system as follows. T is equal to the sum, very simply, of the Ti, okay? The kinetic energy of the system is the sum of the kinetic energy of each body composing the system, okay? Okay, now, since there are no constraints to enforce, since all of the Q's, that's to say, are independent, no constraints to enforce, we can directly adopt Lagrange equations. Okay? And they read like so, as we have seen. Of the kinetic energy, and the kinetic energy we have seen is like this now. Right? Minus the partial derivative with respect to the Q's, again, of the kinetic energy. No. This. Okay. And this, if you do, of course, the derivations, becomes m q double dot transposed minus a vector that we can call qv transposed minus qe transposed. So you see, this basically comes from here. Okay, this basically comes from this first term. Why? Because first of all, we have that m depends on the q. We have seen it. Because, for example, m theta theta depends on the orientation. We have seen it. It's nonlinear in the orientation, but it's not dependent on the velocity of the orientation. Okay, so basically, when I do this derivation, what I get is m q theta. Okay, then I derive it with respect to time, and we have seen that in fact, if the body is rigid, okay, the body is rigid, and if there is basically if the frame is located at the center of mass, we have that the derivation in this case applies to the vector of generalized coordinates, which becomes the vector of generalized accelerations. Okay. So this basically comes from this first part. But then, as we have seen, there is also a part which m depends on time. Okay. Let's do this, all the passages. Let's all the steps. Okay, so this becomes of what? This becomes okay, and all the rest basically says let's keep it that way. Okay, transposed. Now, when I do this, both of them, they do depend on time. We have seen it. Okay? So this becomes as follows. We have the first derivation with respect to m. This is in fact, sorry, but this is transposed. Okay. Then we have the second part, which is this one, the derivation of m with respect to time. Okay. And then we have the last part here. Plus okay, equal to 0 transposed. Oh, now this one we call all of this QV transposed. Okay, actually minus QV transposed. okay? So that we eventually get please note that I removed all the transpose here, okay? Where QV is minus m dot q dot transposed, sorry, not non-transposed, plus all of this transposed, okay, only the last part, okay. And this one here, they are called the quadratic velocity vector. And it accounts for what? Centrifugal effect we have Coriolis effects encompassing here, okay? So basically this quadratic velocity vector, so these are the external forces, QE. This QV instead, which is this vector here, accounts for, we will see it later on, what are called centrifugal effects and Coriolis effects, okay? So if we state that Q is equal to QV plus QE, you eventually get the very famous equation, okay? In a sense, this should remind you of the second law of Newton, right? Force equal to mass times acceleration, right? But in this case, we have a mass matrix, okay? So basically, this basically shows you how a code works, a numerical code, because you choose your Lagrangian parameters Q. It defines a mass matrix, okay? It defines a vector of generalized forces plus eventually your quadratic velocity vectors. And how is it solved here? You have to do this equation in order to get the Q. Of course, you have to get as initial condition the Q dot 0 and the Q of 0, the initial conditions. With this, you are able to basically determine the trajectory and the orientation through time of your body while moving. This is what your code does. This is what Adams will do. Okay, and we will see it in next lecture. Okay, that's all for today.